Hello students, so we were discussing about the n-dimensional Euclidean space e to the power n. Okay, so as you can recall, it consists of the set r to the power n, which is the set of ordered n tuples of real numbers, together with the vector addition, which we have defined, together with a scalar multiplication, which also we had defined, and together with a distance function, which we have already defined. Okay, so e to the power n consists of these say mathematical ideas, right, of a set, a vector addition, a scalar multiplication, and a distance function. Okay, so this totality of all this is called the n-dimensional Euclidean space. Okay, so in today's lecture we will try to understand some basic concepts like linear dependence and independence of vectors, then the basis of this r to the power n or e to the power n, and say linear combinations, how to express a vector as a linear combination of other vectors. Okay, so these things we will try to understand. So for the time being, let us start with a very simple example. See, if I take something like so let us consider e square only, or r2. Okay, e square or r2. So in that in this, say if I have some ordered pair xy in r2, can I use the vector addition properties to write it something like this: x plus 0 comma 0 plus y. Okay, and then I write it as x0 added with 0y. Okay, is it working fine? It is in agreement with whatever we have defined as vector addition, right? So xy in r square, it can be written as x0 plus 0y. Okay, or in our notation we can say x1 x2 in r square, this can be written as x1 0 plus 0 x2. Okay, this can always be written, right? And in the next step I can take this x1 outside by property of the scalar multiplication. So x1 into 1 0 plus this will be x2 into 0 1. Okay, so what I have done, I have written this vector in r square as a scalar multiple of this 1 0 plus scalar multiple of 0 1. Okay, so I have used two vectors to write the vector x1 x2, okay, in r2. So can we do that for x1 x2 x3 in r3 also? Okay, so in r3 how I can write it? I can write it as x1 0 0 0, okay, and then x0 x2 0, and then I can write this one as 0 0 x3. Okay, this can be written in r3, or I can write it as x1 into 1 0 0, x2 into 0 1 0 plus x3 into 0 0 1. Okay, so this is always possible, right? So this type of expression, writing one vector as a sum of scalar multiples of other vectors. Okay, so this is what this is a sum of scalar multiples of other vectors. Okay, scalar multiples of other vectors. Okay, other vectors. So this way of writing is actually called a linear combination. Okay, so we say that it's a linear combination of the vectors 1 0 0 0 1 0 0 0 1. Okay, it's a linear combination of these vectors. Okay, so that means we take scalar multiples of the vectors and then add them up. Okay, so whatever we get, that sum is, or that vector is called a linear combination of the other vectors. Okay, so let us try to define this formally. Linear combination. Okay. So in r to the power n, so let us start with some vectors in r to the power n. Let say we denote this with x1, x2. So remember, this x1 itself is a vector. So x1 is something like x11, x12, x13, like that. X1, x2 up to say x something like xr. Be vectors, or in LPP usually we use the term be points in e to the power n. Okay, that is n dimensional Euclidean space. Okay, so x1, x2 up to xr, each of these is a point in e to the power n. That means what? Actually, this means that x1 is actually a ordered n tuple. So it's something like x11, x12, x13. Okay, that way it goes up to x1n. Okay, so something like that. So in xr is something like xr1, xr2, xrn. Okay, so something like this. So these are points in e to the power n. Okay, let lambda 1, lambda 2 up to lambda r, okay, be belong to R. Okay, so this be scalars. So I told you last day that elements of R will be called scalars in our theory. Okay, then the vector lambda 1 x1. Okay, I multiply x1 with lambda 1 and then lambda 2 x2 plus dot 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 up to lambda n xn is called a linear combination of x1, x2 up to xn. Okay, right? So a vector x in say this, it will be linear combination if x is written as this, where these are scalars. Okay, so this is linear combination of this these vectors. Okay, so so we say that a vector x in r to e to the power n is a linear combination of x1, x2 up to xn, or say xr in e to the power n, if what happens, if we can find scalars, if there exist scalars, say lambda 1, lambda 2 up to lambda r, such that x is equal to lambda 1 x1, lambda 2 x2 up to lambda r xr. Okay, so if this happens, then we say that the vector x is a linear combination of these given vectors. Okay, if we can find some, means if x can be written as some scalar multiples, means as sum of some scalar multiples of x1, x2 up to xr. Okay, so this is called a linear combination. For example, already we have seen 2, 3 is a linear combination of these vectors 1, 0 and 0, 1. Okay, say 2, 3, it can be written as 2 into 1, 0 plus 3 into 0, 1. Okay, so that's simply we can write it this way. Okay, similarly 2, 3 is also a linear combination of say I use some other vectors to express this one. Okay, so say something like minus 1, 0 and say 0, minus 1. Can I write it this way? Can I write 2, 3 as a linear combination of minus 1 0 and 0 minus 1. So how do I write? I can just very easily write it as minus 2 times of minus 1 0 plus, here I can write minus 3 times of 0 minus 1. Okay, so if you just apply scalar multiplication rule, minus 2 into minus 1 will be 2, and here also minus 3 into minus 1, this will be 3, so it will be 2 0 plus 0 3, that is 2 3. Okay, right, this is 2 3. So 2 3 is also a linear combination of these two things, right? Okay, so a particular vector can be expressed as a linear combination of various vectors. Okay, say I can write something like 2 3 is a linear combination of the vectors say 1 comma 1 and say 0 1. Okay, so how do I write 2 3? 2 3 can be written as 2 into 1 1 plus, see, 2 into 1 1, so I have got 2 comma 2, but I need 2 3 here, so just 1 into 0 1. Okay, so it can be written as this. So here what is your lambda 1? Lambda 1 is 2 and lambda 2 is actually 1. In this case lambda 1 is minus 2 and lambda 2 is actually minus 3. Okay, so that's how we write linear combinations, okay, of vectors, right? Okay, so yeah, so one thing let us try to see, if I have a vector 2 3 in R square, okay, or E square, and if I have this vector say 4 6 in R square, can I write a linear combination of these two? Okay, can I write some linear combination of these two which will give us the 0 vector, right? So you try to understand this. I have these two vectors in R square. Can I write it as a linear combination, or can I write a linear combination of 2 3 and 4 6 such that the linear combination gives us or evaluates to 0 0? So just if you use your calculation ideas a little bit, you can see if I multiply this with 2, actually I get 4 6, and I multiply this with minus 1. Okay, so 2 into 2 3 plus minus 1 into 4 6, this will exactly give us 0 0. Okay, so in such situations we actually say 2 3 and 4 6 are linearly dependent. Dependent, right? Means we can find scalars which are non-zero. Okay, at least one of them non-zero, right? This, out of these scalars, at least one of them should be non-zero. Okay, otherwise it's all means 0 2 3 plus 0 4 6. Okay, this always gives us 0 0, so there is nothing special about it. Okay, if I just take all the scalars to be 0, then the sum is, the linear combination is always going to be 0. Okay, but so what is special is can there exist scalars such that at least one of them is non-zero, but the linear combination comes out to be 0 0. Okay, so if that happens, then these two vectors are said to be linearly dependent. Okay, dependent on one another, right? So let us try another one, say something like 1 0 and 0 1. Okay, can we find some scalars such that this scalar into this plus another scalar into this will give us 0 0. Okay, of course one answer is 0 into 1 0 plus 0 into 0 1. This will give us 0 0. Okay, this is always true for whatever be the vectors. Okay, this is always true. Now the question is, can I find some other scalars? Okay, instead of both the scalars being 0, can I find some other scalars which also satisfy this? Okay, so say some scalars like lambda 1 into 1 0 plus lambda 2 into 0 1. Okay, this has to be 0 0. Okay, so can I find something like this? Okay, can we find okay. So lambda 1 into this plus lambda 2 into this has to be 0 0. So to simplify this, let us use this property of scalar multiplication. So this actually reduces to lambda 1 comma lambda 2 equal to 0 0. So by equality of ordered pairs, so two ordered pairs or two ordered n-tuples are equal if their corresponding coordinates are equal. Okay. So here if such a thing happens, then lambda 1 has to be 0, lambda 2 has to be 0. So that means this is the only possibility. Okay, this is the only possibility, right, for these two vectors 0 1 and 1 0. Okay, or 1 0 and 0 1. This is the only possibility that the linear combination will be 0 only when the scalars are taken all zeros. Okay, so such type of vectors, they are said to be linearly independent. That means we cannot find a linear combination with at least one non-zero scalars such that the linear combination evaluates to zero vector. Okay, so that is not possible. So here we say that 0 1 and 1 0, they are actually linearly dependent, linearly independent. Okay, we cannot find a linear combination of them which evaluates to 0. Okay, with all with at least one scalar being non-zero. Okay, if all the scalars are 0, that's obviously the linear combination is 0. Okay, but the important thing is that can we find scalars with at least one non-zero scalar such that their linear combination becomes 0. Okay, right. So say something like 1 2 and say 0 1. Okay, are these two linearly independent? So how will I check? Let lambda 1 into this plus lambda 2 into this equal to the 0 vector. Okay, so what I have to check? I have to check whether there exist or can I find some values of lambda 1 and lambda 2 with at least one non-zero such that this equation is satisfied. Okay, if we can find that, then these two vectors are linearly dependent. If we cannot find, they are linearly independent. Okay, means if we cannot find means if both the scalars turn out to be 0. Okay, then we can say that these two are linearly independent. Okay. So if I just apply the properties of this vector scalar multiplication, this will be 2 lambda 1 plus lambda 2. This quantity has to be equal to 0 0. So by equality of ordered pair, lambda 1 equal to lambda 1 easily evaluates to 0. Okay, if I compare this first and first coordinates, compare the second coordinates, what do you get? Lambda 2 plus 2 lambda 1 equal to 0. Okay, but lambda 1 is already 0, we have evaluated, so lambda 2 is also 0. So this type of linear combination will be 0 only when, or if and only if both the scalars are 0. Okay, so we say that 1 2 and 0 1, they are linearly independent. Okay, linearly independent. Okay, of course we'll define it formally. So say first let us define linear dependence of vectors. Linear dependence of vectors. Okay, vectors in say e to the power n, right? So the vectors x1 x2 dot up to say xr in e to the power n are said to be linearly dependent if there exist scalars lambda 1 lambda 2 up to lambda r with at least one non-zero. Okay, with at least one non-zero. Okay, at least one of these scalars is non-zero, with at least one non-zero, such that lambda 1 x1 plus lambda 2 x2 plus dot 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 up to lambda n xn equal to 0. 0 means this 0 vector, okay, where equal to 0, where this O is the 0 vector, belongs to r to the power n is the 0 vector. Okay. So all coordinates are 0. Okay. So vectors x1, x2 up to xr so belong to this. Sorry, this will be r, lambda r xr. So just correct it. This will actually be lambda r xr. Okay, because I do not know how many vectors I have taken. The number of vectors can be different from n also. Okay. So these vectors are said to be linearly dependent if there exist scalars lambda 1, lambda 2 up to lambda r with at least one non-zero, such that lambda 1 x1 plus lambda 2 x2 plus up to lambda r xr is 0. Okay. So then these are said to be linearly dependent. So for example, in r square, already we have done this example, or say in e square, say 2 3 and 4 6 are, or let me take some other example, say something like 3 4 and 9 12. Okay, 9 12, right? 3 4 and 9 12 are linearly dependent. Okay. So how will you show this? So for small vectors, these are quite simple. See, this is 3 4, this is 9 12. If you observe carefully, this is obtained by multiplying 3. So 3 into this plus minus 1 into 9 12. Okay, what does it evaluate to? This evaluates to, this is 9 12 and plus this is minus 9 minus 12. Okay, so if I add them, this is going to be 0 0. Okay, so but here the scalars are non-zero. Okay, 3 is non-zero, minus 1 is non-zero. Okay, but the scalars, so ultimately we have being able to find scalars lambda 1 lambda 2 such that lambda 1 into this plus lambda 2 into this is 0. Okay, even though lambda 1 and lambda 2 are themselves non-zero. Okay, right? So 3 4 and 9 12, they are linearly dependent. Okay. Another example, let's say for in r e to the power 3, say something like 1 2 3 and 0 1 minus 1 and 1 3 2, okay, are linearly dependent. Okay, right? So you try to observe. If you observe nicely, this plus this gives you this, right? 1 2 3 plus 0 1 minus 1. So 1 plus 0 is 1, 2 plus 1 is 3, 3 minus 1 is 2. So the sum of these two is the third one. So here we can, so I will not write exactly the solution. The solution is, the mechanical way of solving is bit different. Here I have made the question, so it's easier for me to write. So observe that is 1 2 3 plus 0 1 minus 1 plus minus 1 into 1 3 2. Okay, this always comes out to be 0 0 0. Okay, so this is 1 into this. This is also 1 into this plus minus 1 into this. So this comes out to be 1 3 2 plus, and this comes out to be minus 1 minus 3 minus 2. So the sum of this 2 will be 0 0 0. Okay, so but the scalars, you see, the scalars here are non-zero. Okay, it may happen that one of the scalars is 0. Okay, that may also happen. Say for example, say 1 2 then say something like minus 3 minus 6. Okay, and say 5 7. Okay, are linearly dependent. Okay, so here you see 1 2, if I multiply this with 3 plus 1 into minus 3 minus 6 plus 0 into 5 7. Okay, what does it become? It becomes minus 3 minus 6 plus, oh sorry, what did I do? I can just do it with 3. Okay, so 3 into this plus this. Okay, so here what I am getting is 3 6 plus this is minus 3 minus 6 plus 0 into 57. So this is nothing but not 57, sorry, 0 into 0 to 57. This is 0 0. So this is nothing but 0 0. So here you see one of the scalars is 0, but the other two are non-zero. Okay, so this is exactly what I want. There exists, means if you see the definition here, the vectors this are said to be linearly dependent if there exist scalars lambda 1 lambda 2 up to lambda r with at least one non-zero. Okay, at least one of them should be non-zero, such that this linear combination is itself 0. Okay, so that is the definition of linear dependence. And similarly we will try to define what is linear independence. Linear independence of vectors. Okay, so we already have the definition of linear dependence. So linear dependence says that there exist scalars, not all zero, means at least one of them non-zero, with at least one non-zero satisfying lambda 1 x1 plus this is this up to lambda r xr equal to 0, right? So what is the negation of this? I want the definition of linear independence now. I have the definition of linearly dependent. So the vectors are linearly dependent if there exist scalars which satisfy something. So what will be the negation? Negation is linearly independent if for every scalars this particular thing is not true. For every set of scalars that we take, lambda 1 lambda 2 up to lambda r, this particular thing is never true, that lambda 1 x1 that at least one of them is non-zero, and lambda 1 x1 plus up to lambda r xr is 0. Okay, so what does it mean that this is not true? This is not true means at least one of them is non-zero and this is equal to 0. It is not satisfied means what? That this quantity is 0, but none of these scalars are non-zero. Okay, the opposite or the negation of at least one is non-zero is what? At least one non-zero, the negation will be none of them is non-zero. Okay, means everything is 0, right? Okay, so there exist scalars with at least one of them non-zero and satisfying this is equal to 0. So so the negation will be for every scalars lambda 1 lambda 2 up to lambda n which satisfy this. Every scalars which satisfy this ultimately gives us that each of those scalars have to be 0. Okay, means those scalars cannot be non-zero, right? Non-zero scalars cannot satisfy this. Okay, so that is what we will write for linearly independence in this case. Okay, so these vectors are said to be linearly independent. Yeah, so the vectors x1 x2 up to xr belongs to e to the power n are said to be linearly independent if if lambda 1 x1 plus lambda 2 x2 up to lambda r xr equal to 0 implies that lambda 1 equal to 0, lambda 2 equal to 0 to lambda r equal to 0. Okay. If for any scalars, lambda 1, lambda 2 up to lambda r in capital R, lambda 1 x1 plus lambda 1 for any scalars, this with lambda 1 x1 plus lambda 2 x2 plus up to lambda xr equal to 0, gives, if for any scalars lambda 1 lambda r with lambda 1 x1 lambda equal to 0, gives lambda 1 equal to 0, lambda 2 equal to 0, lambda r equal to 0. Okay, write it in a proper language. This if and only if the only set of lambda I for which this is equal to 0 be lambda I equal to 0, then the set of vectors is said to be linearly independent, right? Or let me write it in a better way. If this is said to be linearly independent, is said to be linearly independent if given any scalars, lambda 1 lambda 2 up to lambda r. So in R the following is true. Okay, the following is true. Okay, what is true? Lambda 1 x1 plus lambda 2 x2 plus lambda r xr equal to 0 implies lambda 1 equal to lambda 2 equal to equal to lambda r equal to 0. Okay, so given any scalars lambda 1 lambda 2 up to lambda r, the following is true. That is, what is true? If this happens, if lambda 1 x1 plus lambda 2 x2 lambda r xr equal to 0, then this will also happen. Lambda 1 equal to lambda 2 equal to up to lambda r equal to 0. Okay, right? Given any scalars lambda 1 lambda 2 up to lambda r, the following is true. Okay, this implication is true, right? So any linear combination of this x1 x2 up to xr which calculates or evaluates to 0 means that each of these scalars are 0. Okay, right? So we cannot find non-zero scalars whose linear combinations give us 0. Okay, so that is the basic idea. So for example, this 1 0 and 0 1 are linearly independent sets in E square. Okay, so how do you show this? Let lambda 1 into 1 0 plus lambda 2 into 0 1 equal to 0 0. Okay, we assume that this linear combination comes out to be 0. Okay, so if the only solution for lambda 1 lambda 2 are 0 and 0, then this set is, or this these vectors are said to be linearly independent. Okay, if we get some non-zero solutions for this equation, then the vectors are linearly dependent. Okay, so here actually if we just compute, this actually gives you lambda 1 lambda 2 equal to 0 0. So if you compare, it's lambda 1 equal to 0, lambda 2 equal to 0. Okay, so any relation of this type actually implies that the scalars have to be 0. So this 1 0 and 0 1, these are linearly independent. Okay, so these two are linearly independent vectors. Okay, right? So similarly you can actually show, say, something like this: 1 5 and say 1 5 with say 2 3 or 2 1. Okay, 1 5 and 2 1 are linearly independent. Okay, so how do I show this? Let lambda 1 1 to 1 5 plus lambda 2 into 2 1 is equal to 0 0. It's the 0 vector in R2. Okay, so from here I get lambda 1 plus 2 lambda 2 equal to lambda 1 plus 2 lambda 2, 5 lambda 1 plus lambda 2. Okay, this is equal to 0 comma 0. Okay, so if you compare, you have something like lambda 1 plus 2 lambda 2 equal to 0 and 5 lambda 1 plus lambda 2 equal to 0. Okay, so now try to solve this 2. Try to solve, you multiply this with 2 and this multiply this with 2. So if you solve it, if you just subtract, it is 9 lambda 1 equal to 0. So that means lambda 1 is actually 0. Okay, or and also from the first equation we will get 2 lambda 2 plus 0 equal to 0. So from there lambda 2 also evaluates to be 0. Okay, so any relation of this type or any equation of this type, lambda 1 into 1 5 plus lambda 2 into 2 1 equal to 0 0, actually implies that the only possibility is the scalars have to be 0. So that means these two are actually linearly independent. Okay, we cannot find scalars whose linear combination means we cannot find scalars such that linear combination of the vectors with those scalars evaluates to 0. Okay, that is not possible. So these two are actually linearly independent vectors. Okay, so there are other several examples as well, which probably I won't be able to cover in today's lecture. So in the next lecture we'll discuss more about this linear dependence and independence, because we need to understand this concept first in order to discuss the basic feasible solution, etc. Right? Thank you.